this week we have Ashwinee Panda from UMD now, recently graduated from Princeton, and he's going to be telling us about privacy auditing of LLMs.
Thanks, Thomas. So, hey, everyone. I'm Ashwinee. You may have seen me a bit before. So this is some work done with my collaborators, including Milad and Chris here at Google, and we're trying to do privacy auditing of LLMs. So how this talk is going to look is I'm just going to go over the background and why we believe this is an important problem, and then cover some of the methods that we've used. And by the end of the talk, I hope to give you some insight into how we can actually do privacy auditing for LLMs, meaning that we can actually determine some empirical privacy leakage with a lower bound that is maybe somewhat close to the upper bound that we might get from differential privacy, or what we might expect to see in sort of the worst case. So I'll just start off with some intro that I'm sure everyone here knows. So I think there are a lot of reasons why today's LLMs might seem untrustworthy, and one of them is a line of work, of course, from this group at Google, showing that a lot of training data can be extracted from these models. And certainly, model releases recently, like Palm and Gemma and Gemini and Llama 3, have tried to look at the memorization in their models. And generally, they conclude that their models don't memorize very much data at all. And they do this in sort of the same way throughout, which I'll get to later on. But I think that this kind of tends to underestimate the worst case effects of what happens when you actually did memorize some data. So in other words, just looking at average case memorization maybe isn't enough to tell us how much data we're memorizing in the worst case. And that can have legal consequences, but it also has consequences on the people who are actually offering their data up for training. And one of those consequences is that if we look at the amount of data that we're able to scrape according to robots.txt restrictions across the web, the amount of training data that we have available for training is actually decreasing over time rather than increasing, because more and more websites are being sort of wary that their training data is going to be scraped into an LLM, and then that LLM is perhaps going to memorize their data. And so I think it's pretty much in everyone's best interest to try and actually estimate the privacy risks of our models. And in short, we'd like to be able to know, before we start a training run, what could happen, how much data could our model memorize. And the reason why we might want to know that beforehand is because it tends to be a little bit tricky to remove memorized data after the model has been trained on it. Methods like machine learning have tried, but I think it's still a bit of an ongoing work of progress. And we also are probably interested in seeing how much did our model memorize on some data set. So if we know, for example, that we have this section of New York Times articles that we've trained on, we don't need to sort of hypothesize about the possible memorization. We can just go and see how much our model memorized on that data set. And the reason why we need to do these things is that if anything goes wrong, or we memorize more than our tolerance, we'd like to be able to fix it. But looking at the average case, I think systematically underestimates these privacy risks. Traditional auditing kind of looks like taking some sequences of random data that we call canaries, and then inserting them into normal data. So here the canary data is yellow, and the normal data is blue. And we're at a high level trying to ask the question of whether the model has memorized the canaries, which typically are just random strings. And so the reason why we typically do privacy auditing this way, by inserting canaries into the training data set, is that we really have a lot of flexibility on what the canaries can look like. Easy or hard to memorize, or as is pretty common, the canaries just come from your training data distribution. And this is sort of the average case that I was talking about. So I'm mostly going to be focusing on the worst case and sort of comparing it to what happens in the average case of auditing. And our baseline here is going to be these sort of random canaries that is used in a lot of memorization analysis. And here I'll just sort of look at what some of that prior memorization analysis has done. So here from the Palm 2 paper, they're looking at these randomly generated canaries that are sort of inserted into the training data set, and they have various languages. And the lowest number of repetitions that they observe will actually induce some canary memorization is 5. And we are going to do something a little bit different from that. We're actually going to consider canary sequences that aren't repeated, because we know that we can kind of deduplicate training data. And so this means that we're only going to consider canaries that are present once in the course of sort of a training run. And when I say once, I just mean like sort of probabilistically, because we are going to be randomly Poisson subsampling our data, as we typically do when we train models with DP. And so we're just going to say, okay, with high probability, we don't think that a lot of canaries are going to be selected many times. And we think that it's very unlikely that canaries are going to be selected this many times. Like nothing should be selected, 5 or 10 times with high probability. And so this is for the memorization of extracted canaries. But of course, I mentioned that all of these papers are doing something quite similar, which is taking a sample of 10,000 random documents from the training corpus, using the first 50 tokens as a prompt for the model, and then measuring the verbatim memorization on sort of some continuation of that sequence. So we're also going to use a 50 token prompt, and we're going to test for the memorization just of the canary. So let me show you a quick diagram of what that's going to look like. And here, instead of looking at verbatim memorization or approximate memorization, which some prior work has done, we're just going to simplify things down to membership inference. So we're going to take sequences of normal data, normal documents from our corpus, and we're going to append some canary sequences to it. So these canary sequences may just look like these random tokens, or they may look like something else, which I'll get to. And now, once we have these sequences, I'm going to abuse notation here a little bit, and I'm going to call this complete sequence overall as being a canary. So canary is some regular text ending with a canary. And I can't see the chat, so if anyone has a question, hopefully somebody will let me know. And we're going to take these canaries, and we're going to pick half of them and actually say that these are members. The rest of them are going to be non-members. And we're going to insert those into the training data set. And then we're going to train on a mix of the normal data and the canary data. So again, I'm going to be calling multiple things canaries. The canaries, the tokens, are specifically these weird tokens here that I have denoted with the yellow dots. I call those canaries. And I'm also going to call the overall sequences canaries. Peter asks, train from scratch. That's a great question, Peter. I'm going to get to the data set in the experimental setup. So this is what we're going to do for the training procedure. And the goal here is whether we can distinguish members from non-members. So specifically, we're looking at this sort of membership inference attack where we create these canaries, and we're inserting half of them as members and then training normally, or with DP in our DP experiments. And there are a lot of actual membership inference attacks that you can do. We're going to do something very, very simple. We're just going to evaluate the loss of the model on all the canaries and then just use the loss to distinguish between members and non-members. There are more sophisticated things that we can do, but since we're primarily measuring the way that we create canaries and not sort of the actual membership inference attack itself, we sort of defer those, although I can talk about that if people are interested, and we just sort of look at the loss. So this is sort of the regular way that you might create canaries. And it turns out that in our setting, this does not tend to work very well. Something that is perhaps a little bit stronger is saying that each canary has some unique token that's not seen in the rest of the data set. And we hope that by doing this, we can increase the power of our membership inference attack a little bit. So, this is, some example here where maybe the canary data has a character that is in one of the multilingual parts of the tokenizer, and our training data set perhaps doesn't contain this. So we're saying that it's going to be much easier to tell whether these sparse canaries are present. And there are a few different ways that we can create these sparse canaries. the motivation here is not only that there is going to be one row in the embedding matrix, which should only really get updated strongly with this token, but also that there are going to be far fewer data points from the rest of our training data set that are sort of overwriting our canary. So a very simple way to do this is sort of with this random baseline. So we're going to just select a token at random that's not present in our training data set, and we're going to append this token into normal sequences of training data. So at this point, you might guess that this only really works for fine-tuning, and you would be correct. All the experiments that I'm going to show you here today are fine-tuning pre-trained LLMs on some language model dataset, and that's primarily a factor of the compute limitations that we have in an academic setting. And I'll talk a little bit about some future work where we can extend this to pre-training. And here, if we have a fine-tuning data set, we can just build a unigram model over our fine-tuning data set, see what tokens aren't present there, select one of those tokens, and then just append that to the normal sequences of training data. And because there are actually plenty of sequences, plenty of tokens that are only present once in a given training data set, I think it's reasonable to say that these canaries sort of estimate the average case privacy leakage of an outlier. Another way to do this would just be by identifying sequences that actually contain a token that is only present once and using those as canaries. But I prefer to actually look at the canary insertion setting. Still, I don't think that this is that unrealistic, because in these fine-tuning data sets where we do fine-tune LLMs a lot of the time, there are plenty of tokens that are only going to be present once. Now, this sort of estimates the average case privacy leakage. And this is a pretty easy baseline to use. But we might want to look at sort of a upper bound. So if this is our baseline, we want to see how strong our canary could possibly be. And for that, we're going to propose a different canary. So this we're going to call the new token canary. So here we're going to actually use one of the unused special tokens in the tokenizer. So the tokenizers for some of these models, for example, Llama 3, has a lot of special tokens that were just created, never trained, and they basically just have some default value that they're initialized with. And these models are released this way because it's pretty useful to have special tokens that you can use for things like metacognition, adding a thinking token for approaches like star or quiet star, or tool calling or some other stuff. Now, if these special tokens don't exist, don't worry about it. It's pretty easy. You just add a new token to the tokenizer and modify the model's embeddings appropriately. And once again, you're going to take this token and append it into normal sequences of training data. Now, this is quite a bit stronger than the random token canary, because not only is this a token that hasn't been seen in the rest of the fine-tuning data set that we're about to look at, it also hasn't been seen anywhere else in the model's entire pre-training data set. So in other words, our model should assign basically zero probability to ever generating one of these special tokens. And as a result, it should be very, very easy to tell if our canary contains one of these tokens, whether or not that canary was actually in the fine-tuning data set. And we like to think that this is something that a model developer can do kind of easily, because if they want to see, all right, I have a pre-trained LLM, now I would be interested in seeing how much this could possibly memorize if I fine-tuned it on something. Or even if you're training from scratch, you can also do this, right? You can say that I'm going to create my model. All of the embeddings are going to be randomly initialized to whatever their initialization is. And some of those tokens are only ever going to be used for a canary sequence. And after you do this training process, you can just reset the embeddings of these special tokens, and you're going to maintain the performance of your model. And we have found that empirically this does maintain the performance of our model. And the purpose of this new token canary is really to estimate the worst possible privacy leakage. So the absolute worst case scenario, if I'm thinking really about DP, is that the difference between my dataset D and the other dataset D prime is that by moving across to this adjacent dataset, I've entered a world where there is now a token that was never ever seen in my current data set. But also, this new token canary factors in the pre-trained model. So moving from D to D prime and seeing a new token, that's also accounted for in our random token canary. But this sort of DP for fine-tuning LLMs methodology has a little bit of a gap in that it doesn't consider how the model's pre-trained data set would actually influence it. And this new token canary does take care of that. So I'm going to go over some more canary strategies, but first let's look at some results. And I'll just briefly go over the experimental setup here. So we're going to look at a few different model families, and we're going to fine tune on a small sort of chit-chat looking data set. And we can fine tune on sort of other data sets like the common SFT data sets that you might use, but those are primarily LLM generated. So this data set is actually generated from like Amazon Mechanical Turk workers. It's been a popular data set over the years, so we choose this. And we're going to pick 1,000 canaries total, half of which will be inserted into our data set. And our subsampling ratio is going to basically say that 1% of each batch is going to be canaries. So the expected number of canaries that we don't see, if we train for, let's say, 100 iterations and looked at overall 100 million tokens, works out to roughly something such that the expected upper bound on our membership inference attack success rate is about 86%, and the rest of the canaries we probably wouldn't see. I'm only mentioning this because a lot of the plots are going to sort of have this ceiling at around 85%, and this is why.
There's a couple questions in the chat.
Okay, let me look at the questions.
Okay, great.
Okay. Yes, I cannot see the chat because I only have one window here.
Okay, I'm happy to read them out.
How do you pick the normal sequences of training data that you append to? And should we be worried about those sequences having duplicates or near duplicates in the fine-tuning data set? Yeah, great question. So the sort of normal sequences of training data that we append the token to, we're relying here on the just like split between the train and test set. So we actually select data points from the test set, which they say has a distribution shift. So the distribution shift here is sort of at the person level, if you want to call it that. So every sequence here is basically a conversation between two people. Each of these people has some pre-built persona, and the test distribution has different personas in there. So from that, we would hope that there is supposed to be some distribution shift between train and test. At least that's what they say in the paper. And so that leads us to say that the sequences of training data that we're appending the canaries to should not have any duplicates or near duplicates in the actual training data, because they're actually built from different personas, which means that the conversation is going to have like different stuff in here. So by different persona, I mean like someone's favorite TV show is different. So, you know, hopefully that sequence Game of Thrones like should not be repeated. All of this is approximate. You know, we didn't actually analyze the training and test data sets for, matches, but this is some like fairly old and well-used data set. So to answer your question succinctly, Peter, I would say I'm not worried about the sequences that we append the canaries to having duplicates or near duplicates in the fine-tuning data set. Okay, and it would be helpful, Matthew, if there's a question in the chat, if you could just let me know.
Yep, sounds good. I also have a question. Do you mind?
Yeah.
Okay, so in the previous slide, you said something about model performance not being impacted.
Yeah.
Is this just like overall model performance?
Yeah, so we're basically saying that when we fine tune on this data set, we're looking for the model to basically pick up on, how people behave if they have a certain persona. So the persona is sort of the prompt, and then whatever the model ends up generating after that is its prediction of the conversation. And we're just measuring performance very simply as the perplexity on the validation set, which it hasn't seen. And we're just going to say that if we use this sort of new token canary strategy, then after we train, we can just reset the embedding. And this is not actually going to impact the performance as measured by the model's perplexity on the unseen split of this trained data.
That's good. Thanks.
Okay. Let me continue on here. So first, we're just going to look at something very, very simple, which is, all right, let's say I take Gemma to 2B, and I compare these two different canary selection strategies. How are they going to perform relative to each other? And it may not surprise you to see that this new token canary that we have come up with is doing very, very well. Some might even say perfectly well. It really does not have a false positive rate. And the random canaries that we've selected are also doing better than you would expect. So the sort of like true baseline of just selecting actual random tokens that are in the training data set, I'm typically not bothering to plot because it's just always essentially this dashed line. But this dashed line is what happens if you just have canaries that are literally random tokens selected from the training data set, which is that they have absolutely no impact, really. And your membership inference attack success rate is purely random. So on this FPR, TPR, ROC curve, you can think of it as like the true random baseline is just like a dotted line. At least here, the sort of random baseline that we're looking at is still using tokens that are not present in the rest of the training data set. So we at least have that advantage that the baseline that we're using here still is sparse, in that the updates to that embedding, the row of the embedding matrix, should be sparse. Of course, as I've been mentioning, this doesn't take into account the fact that the pre-trained model would have some existing bias going into the fine-tuning process. And so many of these random tokens that we've selected, although they're not actually in this fine-tuning data set, the model may have a already strong likelihood that such a token exists. And so the model would get updates to that row of the embedding matrix. And an example of that is like maybe the random token that we've selected that's not in the training data set is just like some number. And the model does think that like numbers should appear at some point. And if they don't appear, then it just downweights that. So you can see clearly there's a big difference between a new token canary and a random token canary. But probably you would expect this. And of course, who is this new token canary useful for? It's really only useful in the setting where you assume that you are the model developer and you are interested in estimating the privacy leakage of your own model, and you actually have the ability to modify the embedding. So let's perhaps look at something that is in between these two lines. And that's what I'm going to be doing for the next few canary selection strategies that I'm going to be discussing. So let's think of another way that we can implement sparse canaries that is somewhat in between these two things. So we know that it's not sufficient to just select a token that is not in the training data set. And we also don't want to say that we're actually have this ability to select a token that the model never saw before. But what we do want to do is select a token that the model is very unlikely to ever predict. So this is going to be our search token canary. So we're going to, again, sample normal sequences of training data. And for each sequence, we're going to find tokens such that the model's likelihood of ever predicting that token, given the sequence, is minimized. And this is still using, ultimately, tokens as the canary that don't exist in the rest of the training data set. But importantly, here we're sort of being a little bit clever about it and saying that it's not enough for our canary to not be in the rest of the training data set. Also, that canary should not be anything that the model is ever going to predict. So there are a lot of ways to do this. You can use GCG, for example, but we can also just use random search. Now, a couple of caveats here. Of course, actually evaluating this probability requires us to do an inference pass through the model, which means that we do have to have the ability to actually do an inference pass through the model. So once again, we're back in the setting of, okay, you clearly need a pre-trained model to be able to do this. Also, evaluating this search is actually kind of expensive because we have to actually do a forward pass through the model. So instead of that, we can just use a small model like GPT-2 as a surrogate for other models and larger models. And that is actually what we do. Just actually doing the forward pass without sort of making the search clever is a bit expensive. And again, this is some intermediate canary selection strategy that I'm going to show you that is not really the main one that we're going to end on. So this is not something that we bothered optimizing very much. And the point of this token is that it tells us what sequences this model, this specific pre-trained model, is least likely to predict correctly. So the previous to random token canary, that was really model agnostic. And this tells us what sequences this model is least likely to predict correctly. So now if we incorporate these sequences into our fine-tuning data set, we expect to see that updating on these sequences is going to create a difference in loss that is very, very easy to detect, because if we never saw this token, we specifically know that this is some sequence that the model would never have predicted. And if we look at an evaluation of these methods across a decent sort of split of models, we can see that in general, these sparse canaries are performing fairly well. And our sort of ceiling that we talked about earlier, what is really the most that we would expect a membership inference attack to succeed, given that we are randomly subsampling these canaries, that ceiling is pretty much hit by either this new token canary strategy or the search token canary strategy. And indeed, in some cases, one of these is better than the other, and there's definitely some variance here. But I think without getting too much into the analysis of these results and how much this matters or whatever, I think the big takeaway is like, okay, if these canary selection strategies are something that you can actually implement, then you should definitely do it. Like if you're a model developer and you actually have the ability to do this new token canary, you should absolutely do it, because it's very easy and it's going to work pretty much all the time. Here, I'm just giving you a bar plot of the AUC, but we are going to sort of go into the audited epsilon, and there you'll see sort of a bigger difference. And similarly, if you are trying to come up with a canary and you actually have the pre-trained model, you should definitely go ahead and use this search token canary selection strategy, because both of these are fairly easy to do, given that you actually have access to the ability to edit the model or a pre-trained model, and they tend to outperform the random token baseline. Again, here there's some variation because we're looking at AUC and not sort of what we really care about in an auditing sense, which is this actual privacy leakage. But we'll see when we look at the actual ROC curves, as well as the actual audited epsilon later on, that in fact the difference between sort of the new token canary and the random token baseline is perhaps much larger than we would think by just looking at the AUC. This just happens to be a convenient way to look at it.
There's a question in the chat. What is the intuition/evidence for using natural sequences as prefixes? Would it be weaker to random strings or special tokens in the prefix?
This is just a setting that I'm showing you right now, and then I will have a slide where I ablate this and say, okay, now here's what happens if the prefix is some random string, and here's what happens if the prefix is something that we've sort of handcrafted. I just figured this was a useful baseline setting to show, and then we'll keep ablating things and ablating things and ablating things. All right, we're sort of at the halfway point here, so I'm going to just pause and summarize what we've shown so far. Fun unrelated fact: I love using the PowerPoint designer for the slides, and it just makes random little images, and it just selected these random birds for me, which I thought was cool because it at least knew that these were canaries. I don't know, it's not AGI. So only model developers, right, can use this new token canary, and that's because this is the worst case privacy loss. A sequence contains a token that's not seen anywhere else, not just in the fine-tuning data set, but the entire pre-training data set. So really, this is the worst case privacy loss, and it's only for model developers. Then the search token canary. So this is something that you can only use if you have black box access. If you can't actually run a forward pass on the model, for example, if you're doing pre-training and the model doesn't exist yet, then you'll have no idea what token sequences are good canaries. And black box access, tends to be a somewhat realistic assumption. You'll see a lot of times that papers will assume they have black box access, and they'll run sort of some adversarial prefix finding attack like GCG, and then they'll show that it transfers over to other models. And indeed, we just showed that our search token canaries transfers fairly well from GPT-2 to other models, both in GPT-2 and outside of that model family. But it still requires black box access to that model. And then you have the random token canaries, which don't require really anything, and also don't seem to do very much. So we'd like to create a method that doesn't require what we say a model. So the new token canary and search token canary, in some sense, require you to actually have access to a model. So we want to create a model-free method that is still effective. And that's going to motivate the final canary selection strategy that we talk about. So in some sense, this random token canary was kind of like a unigram model over our data set. We just said, all right, here are all of the tokens that exist in my fine-tuning data set. Now give me a token that is not in this fine-tuning data set. And naturally, in a unigram model, the probability that's least likely to be predicted from that unigram model is just any token that's not actually in that fine-tuning data set. But we can sort of level up a bit and try and create a bigram model. So we can fit a bigram model on our data set by just looking at all of the sequences and then saying, all right, X was before Y here, so I'm just going to increase that count by 1. Our bigram model is just a 2D matrix of size, vocab size, vocab size. And the reason why we need this model is that we'd like to find a canary sequence such that the probability of that final last canary token is very low given the data that comes before it. And what we're going to do here is we're going to say that we're actually looking for 2 tokens, right? So in this setting, we're saying it's perhaps not sufficient to just insert like 1 token that is very unlikely, because that token that's unlikely is just actually going to be something that's not in the fine-tuning data set. Because of course, this bigram model is only going to be fit over our fine-tuning data set. So this still doesn't have any knowledge of our pre-training data set. And so it's still going to be sort of falling short. But in addition to having a final token that is unlikely to be selected, we also need it to be unlikely selected conditioned on the previous tokens. And that's where our bigram model comes in and says that the probability of Y given X should be very low. So after we build this bigram model on our fine-tuning data set, we're just going to directly mine the sequences that we believe are going to make for good canaries. So from the looking at the results of the random token baseline and the search token canary and this new token canary, we have a sense that we want some X that is unlikely and then some Y that is unlikely given X. So you can think about it very simply as for every X that is unlikely, we're going to pick the least likely Y that was so far unseen. And this is going to get us a little bit closer to that search token canary. It's going to account for somewhat the relationship between tokens, at least as far as a bigram model can actually approximate a full model that we are training. But again, I want to emphasize this still doesn't have any knowledge of the pre-training data. So in that sense, it is really quite model-free, or data-free if you believe that the model that we trained is just a reflection of its pre-training data set. So this we feel is somewhat realistic. If you actually have a data set and you want to sort of insert a canary into it, it's very likely that you're going to be able to fit a bigram model on that data set, because fitting a bigram model, even on fairly large text corpuses, is pretty easy to do. So what's going to happen when we actually look at these bigram canaries? So here I'm just going to leave the sort of like new token canary there as an upper bound, and I'm going to have these random token canaries there as sort of a baseline. And it is pretty clear that our canaries selected from this bigram method are going to consistently outperform this random baseline. And that's pretty easy to do because the random token baseline is not really doing anything at all. It's very, very easy to beat. There's still quite a bit left in terms of the gap between this bigram token canary and what we would get if we just selected entirely new special tokens. And I think that's to be expected. because our bigram canary still does not have any knowledge of what is going on in the rest of the pre-training model. And again, we have the ROC curves here across a few different models, and the bigrams are basically the same across these models, except for the fact that these models do use different tokenizers. So we do have to actually tokenize the data set and then build a bigram model on that data set. But the actual sort of bigrams that we select, we randomly pick them every time. The AUCs and the ROCs don't tend to change very much. And also here we see that the AUC is perhaps a little bit deceptive because our random token baseline gets a decent little bit of AUC over in this area where it has a pretty high false positive rate. That's sort of at the top right here. And that region is really not very useful to us for auditing because it's not really going to be good enough for us to, select 10 things and then like half of them are, not really in the actual fine-tuning data set. So this is sort of the last canary selection strategy that we have. And now I'm going to sort of go into some, sort of like hanging threads, miscellaneous ablations and stuff like that. So first, we actually are going to look at what happens if we run an auditing method. So unsurprisingly, this new token canary thing is great for auditing. So we can first do a totally non-DP run just to make sure that our random baseline is actually able to do something. And we can use the privacy auditing method from Steinke and Nelson-Jagielski. And this privacy auditing method is going to give us a lower bound on the empirical privacy leakage with some confidence. So here the confidence is 99%. That the empirical privacy leakage was at least this thing. And the random canary is hardly going to get any privacy leakage at all. You can see here for GPT large that it is getting a little bit, but then again, that goes back down to GPT XL. And it's interesting, I think here as well as when we looked at these AUCs, that there isn't a very strong correlation between the model size and how effective the canary actually is. And to some extent, that's because we're using such a small data set, right? We're only training on about 100 million tokens. But a lot of fine-tuning data sets are actually quite small. If you think about, for example, everyone's favorite fine-tuning data set, GSM-8K, the GSM-8K training data set has 7,500 examples. There are about 500 tokens each. And so you're not looking at billions and billions of tokens for a fine-tuning setting. Billions and billions of tokens, you're getting into perhaps things like Proofpile or StarCoder for code or math continued pre-training. So because the fine-tuning data set is so small, and really it is quite easy, all our model has to do is look at the persona of a person. What do they like? Do they they have some sort of these biographical attributes? And then all it has to do is sort of predict what they're going to say. So given that, perhaps all of these models are very, very over-parameterized for the task at hand. And so we shouldn't expect to see any variation across models. But still, even here, the random canary is really not doing anything. Now, this is for a non-DP run. And the reason why I showed you a non-DP run is because there is nothing to show you for a DP run because the random canary cannot do anything in the actual DP setting. So in a DP setting, we just train a GPT-2 model with some regular privacy guarantee epsilon equals 4, and we get a 99% confidence estimate that the privacy leakage is at least epsilon of 1 using our proposed canary. In the same setting, if we use some random canary, we don't get any audit whatsoever. And this is just one result in sort of one setting. These numbers don't really change much depending on the model. As we showed, really this new token canary does not care what model it's being inserted into. It's just a token that was never seen before and will never be seen after. But I do think it's interesting that we can show some privacy leakage. But even with this, which is really what I would sort of consider like one of the strongest canary methods that I can possibly think of, we don't show that the privacy leakage is, really close to sort of what the limit is. So this method with this particular number of canaries I think it can show, up to like a, lower bound of 3. If you want to have more than 3, then you need to increase your number of guesses or something like that. But we don't really tune the guesses across the auditing. Did you try to train with a larger epsilon? Yes, we did try to train with a larger epsilon. That does increase things somewhat. So I mentioned a little bit of this at a talk I gave at TPDP in Boston. And hopefully that was recorded somewhere and is online. And we go over a few different, like privacy thresholds for DPSGD, as well as another method, a zeroth order method. And we apply this auditing method, and we sort of see how much privacy leakage each of these training algorithms we're able to show the privacy leakages. As you increase the epsilon, like this privacy leakage does not increase that much. And like one part of that is just that like all the sort of hyperparameters that we've like sort of fixed a priori, like the number of canaries that we've inserting, and also the number of guesses that we're making. This like with this number of guesses, even if you're getting everything 100% correct here, you can see that the y-axis here only goes up to 3. So if you wanted to be able to like make an auditing for like 10, you would have to actually guess on more things than 100. We just like don't tune the number of guesses based on the method, because that is kind of, I think, weird. Yeah. Some more, miscellaneous things. So typically, we train with a network prediction objective. That's just sort of the standard thing that we do. But in fine tuning, it's common to use an SFT objective. And in an SFT objective, the prompt is masked and the loss is only taken over the answer. So what are the prompt and the answer here? So I'm going to go way back here to when we actually talked about the training data set. So everything here that you're seeing, this person 1, person 2, all of that is actually the response, as it were. The prompt appears to have been cut off in this slide, but the prompt says that person 1's persona is, okay, I don't have children, and I like Cheetos, and I don't watch TV. And the prompt also says that person's 2 persona is that they have, 4 children, and they like watching Game of Thrones and something like that. So instead of basically having a loss on all of the prompt tokens, we can mask out that prompt. So typically when you do supervised fine-tuning, this is what you're going to do. So supervised fine-tuning, again, if we think about GSM-8K, the prompt is usually going to be like, okay, here is a question, right? And then the entire text of the question. And then it will say like, think step by step, and then give me your answer. And then all of this prompt, which includes the question text, that's going to be masked. So we don't have a loss over this. The only thing that we have a loss over is the answer. So in this case, for our model, it's what we think that people are going to say to each other, given our personas of what the people are. And in GSM-8K, it would be our model's step-by-step response of solving the math problem, given the prompt, which it doesn't take a loss over. So it's important to note that even though the prompt is masked, technically if a canary is there, you could actually get some auditing from that. We don't put the canary in the prompt that we put at the end of the sequence. And we find that doing this sort of SFT style training where we mask out the prompt is going to significantly increase privacy leakage. So here we're looking at the auditing performance of our searched token canary. And we see that although this is not giving us really great auditing results for these models with a next word prediction objective, it is giving us pretty good auditing results when we are actually masking out the prompt. And that does depend on the model. So, the best auditing performance, which is basically at the ceiling of 3.0, is for the Pythia 410M model. And for other models, maybe it's a little bit less. But I think this is worth pointing out because, fine-tuning is typically SFT. And if SFT is a significantly increasing privacy leakage, perhaps that is something that varies a lot across data sets. And we're only looking at this one data set, so I don't make it a big point here. But if this does vary a lot across data sets, then this is probably something that we should keep in mind. The next ablation that I'll get into is what the actual sort of like training method that we have is. So we can train all of the parameters of our model, but if we are doing fine-tuning, we may as well do some parameter-efficient fine-tuning method, such as LoRa, which is low-rank adaptation. And changing the lower rank did not seem to have any impact on the AUC or anything like that. So here again, we have an ROC curve. All the lines are on top of each other as we vary the rank. All the AUCs are basically the same. So what I get from this is that whether you do full fine-tuning or you do lower fine-tuning, these canaries are basically still as effective. Here I'm just showing it for the new token canaries, but we do it for the other canaries as well, and we have a similar conclusion there, which is that changing the LoRa rank does not change the canary impact, and changing from LoRa to full fine-tuning also does not really change any of our results. Now, finally, Galen, I get to your question. So in general, we're assuming that the canary is appended to a sequence of normal data that's drawn from the test set. But that's not the only thing that our prefix can be. So our prefix can also be OOD. That's these first two columns here. And OOD means that it's just random tokens. The sequence can also be in distribution, which means that we actually craft another separate biographical sequence entirely. And so, Peter, this would probably answer your sort of first question, which is that now we really make sure that our sequences don't have any duplicates or near duplicates in the fine-tuning data set by actually just crafting our own biographical sequences just from some programmatic list of attributes. And then we use these and we insert these. And what we can see is that, again, I'll be saying this a bunch of times, but this new token canary does not care at all what is happening. So it doesn't care, what the model is. It doesn't care what the prefix is, because when it comes down to it, there is no way that the model is ever going to predict this special token before it trains on it, and the special token is not anywhere else in the fine-tuning dataset. However, if we don't look at the new token canary and we instead just look at the random token canary, what we find is that actually if the entire prefix, if everything is basically just a bunch of random tokens, which means that your entire sample, your entire document really is just random tokens. And of course, we're prompting the model with the first 50 and then asking it for after that to see for memorization. If that is the case, then actually the random token canary is much better. It's not as good as the new token canary, but certainly it's much, much, much better than if the training sequence is just a biographical sequence like in the percentage chat dataset or some synthetic biographical sequence that we created. So that is really the first line here, the FPR. What is the TPR when the FPR is at 0.1%? And we can see that the random canary, which is this without new column, the second and fourth column, that goes from a 7.4 TPR to a 36.8 TPR. So that's a pretty dramatic improvement when we go from a biographical sequence being the prefix to a set of random tokens as the prefix. So this is just something that we ablate. And so most of my results are in the setting where the prefix is just some regular document from the training data set. But we also have an understanding of how this happens if you synthesize your document or if your document is purely random tokens. And we mostly talk about canaries that are just one or two tokens, but changing the number of tokens in the canary sequence does not change results much, either for random canaries or for the new canaries. And here I'm just showing you the FPR for the new canaries. And when I say the number of tokens in the canary sequence, again, we're always conditioning on 50 tokens as is standard in prior work. And then we're just evaluating the loss over the canary sequence. So in this case, we're training on more of these random or new tokens, and we're also evaluating the loss across more of the random/new tokens, but we are not changing the length of the prompt. We kind of know already from prior work that as you increase the length of that prompt beyond 50 to 1,000 or whatever, then all of these things sort of get a lot stronger. So we don't really look at that much. So finally, I'll just conclude here with some next steps. So we have this bigram procedure for selecting canaries that we think is pretty cool because it doesn't require you to have any model at all. It just requires a data set. It just builds a bigram model over that data set. And then it gives you canary sequences that are actually quite good and can be useful for auditing. But this is a bigram canary that we fit on this data set. So how does this work if we actually try to fit the bigram canary on some other data set and then transfer it to our real fine-tuning data set? This now removes the assumption that the quote-unquote adversary in the membership inference game needs to actually have access to the fine-tuning data set. We're also interested in seeing whether we can actually make these canaries work when the tokens are actually in the training data set. Everything that we showed here, the tokens are not in the training data set, because if you look at a baseline of like random tokens where the tokens are in the training data set, then it turns out to be very, very hard to actually do membership inference, especially for like fine-tuning data sets where the coverage of tokens is quite limited. But if we want to actually extend this out to pre-training, we need to be able to get our strategies to actually work when the tokens are in the pre-trained data set. We have some encouraging results there so far, but we are thinking that perhaps we can come up with another canary section strategy if we say, all right, now all the tokens that we come up with have to actually be in the trained data set. Lastly, we'd like to, after we've sort of figured these things out, we'd like to be able to insert a bigram canary during pre-training. And that would require first fitting this model on a different data set, and of course, without actually training any models. So let's say that you're pre-training on whatever unseen massive data set that Gemma is trained on. Perhaps I could fit a bigram on like one dump from Common Crawl. Everyone has access to Common Crawl. Everyone can download it. And it's perhaps representative somewhat of the Gemma pre-trained data set. And I'm able to select the canaries in such a way that the tokens are actually in the training data set. If I can do both of these things, then I can actually come up with a way for creating these canaries that are going to be inserted during pre-training that are going to be much more likely to get selected than anything else. As a reminder, I talked a bunch about like the random token baseline. Even that random token baseline, because it's using tokens that are not present in the rest of the fine-tuning data set, is much more effective than like actually just selecting random tokens. And in general, I think all the canary selection strategies that we covered here, like whatever these like 4 strategies or whatever, they are significantly more effective in terms of canaries that are useful for auditing than what we had sort of seen in prior work. In that all of these canaries are data space. They don't require you to say that you are able to update the model with a gradient that is sparse, which is, of course, the very successful gradient-based Dirac canary. So all these canaries are data space. All of them, I would say, have varying levels of strengths of the assumptions that they require, but they all work more or less well for privacy auditing. It's just a matter of what threat model or strength of adversary you're considering when you're actually doing this audit. Thank you.